Although often used interchangeably, spectroscopy and spectrometry are two different analytical techniques which differ based on the dual nature of light itself. In spectroscopy, there is an interaction between the particle nature of light and a physical particle. Remember, light is made of photons, and photons have energy, where the energy of a photon is equal to Planck's constant times the frequency. In spectroscopy, the energy of this light is absorbed to induce a transition of equal energy in the matter that's doing the absorption. The highest energy transition involves transitions of electrons between orbitals. This is stimulated by UV visible radiation. Bond vibration transitions are also quantized by the quantum number V. These are activated by the absorption of infrared photons. Finally, the easiest transitions, the lowest energy transitions, rotational state transitions, where the quantum number is J, are produced by absorbing photons in the microwave region. Spectrometry, on the other hand, involves techniques that deal with the interaction of matter and the wave nature of light. Besides being a particle, light is also a wave. It has wavelength and it has frequency. Waves can interact in many different ways. You can have constructive or destructive interference. In this case, with the bond vibration frequency. This produces what is called Raman spectroscopy. Fermions spin. They spin at a given frequency, which can resonate with the frequency of radiation, producing electron spin resonance spectrometry or nuclear magnetic resonance spectrometry. Finally, waves also diffract and reflect. This property is used in X-ray diffraction. All of these techniques will be viewed in detail in the following lectures. How Raman spectrometry works. First of all, radiation propagates at a given frequency. Bonds also vibrate at a given frequency over time. These can be in phase, which would lead to constructive interference, where the frequency remains the same but the amplitude increases. Or the phase of the radiation and the bond vibration through time can be out of phase, in which case the frequency again stays the same, but the amplitudes cancel. In Raman spectrometry, transitions are not the result of the absorption of a photon. Raman transitions are the result of Rayleigh scattering. In Rayleigh scattering, you have an electrostatic scattering of electromagnetic radiation, or light. Light waves interact with particles possessing oscillating polarizability, in other words, a bond vibrating through time. The intensity of the scattered radiation is related to the original intensity by 8 pi to the 4th alpha squared over lambda to the 4th r squared 1 minus cosine squared theta, where alpha is the polarizability of the bond, lambda is the wavelength of radiation, r the dimension of the scattering sensor, in other words, the bond length, and theta is the angle of incidence between the light wave and the oscillation of the polarization. Energy is therefore transferred between the vibrating bond and the photon in Rayleigh scattering. As previously stated, energy waves can interact constructively or destructively. Constructive interference between a photon and a bond vibration is called the Stokes shift. Energy is lost from the vibration and transferred to the photon. Photon exits at a higher frequency and the bond vibrates at a lower frequency. where the new frequency is equal to the original frequency minus the change in energy absorbed divided by Planck's constant. Destructive interference, or anti-Stokes shifts, result in the loss of energy from the photon to the vibration. The photon exits at a lower frequency, the bond vibrates at a higher frequency, where that new frequency is equal to the original bond vibration frequency, plus the energy absorbed over Planck's constant. Lasers are used as light sources in order to provide monochromatic excitement. Both shifted and anti-shifted photons now have slightly different wavelengths than the original radiation. They also differ slightly in their polarization angles. Raman instruments use polarizers to only examine one aspect of the shift. In practical terms, Raman spectrometry results resemble infrared spectroscopy, such as found in the infrared spectrum of diatomic, where you have splitting of the absorption due to rotational changes. Since energy is either added or removed in Raman, the spacing between rotational transitions also changes. However, in rotational spectroscopy, where the photon is absorbed, delta J is 0 plus or minus 1. In rotational spectrometry, where the change is additive, delta J is 0 plus or minus 2. For Raman, the change in the transition of the rotational transition is the E of J plus 2 minus E sub J, which is your rotational constant for J plus 6, where, once again, your rotational constant in wave numbers is equal to Planck's constant divided by 8 pi squared times the moment of inertia times c. A wave number is a reciprocal centimeter, so again remember the value of the speed of light is 2.998 times 10 to the minus 10th centimeters squared per second. Therefore, when you have a rotational change caused by the interaction of light in spectrometry, the spacing between adjacent J values is 4b as opposed to 2b in spectroscopy, and the spacing between the P and R branches is 6b instead of 3b in rotational spectroscopy. Raman spectrometry and infrared spectroscopy on the surface appear very similar. Both involve the measurement of vibrational transitions. The difference between the two can be seen in an examination of carbon dioxide, a linear molecule which has a center of inversion and therefore belongs in the d infinity h point group. For linear molecules, the number of vibrational modes is calculated at 3n minus 5, where n is the number of atoms present. For nonlinear molecules, the number of vibrational modes is calculated at 3n minus 6. Since carbon dioxide has 3 atoms, 3 times 3 is 9. Since it's linear, subtracting 5 means there are 4 modes of vibration. Infrared spectroscopy requires a vibrational mode to have an oscillating dipole in order to be active. This can be seen and explained by looking at the first 2 possible vibrations of the carbon dioxide molecule. Nu sub 1 is an in-plane symmetric bend. One starts with a linear carbon dioxide, but at first the oxygens will bend up, producing a dipole moment pointing up, and then they bend downwards, producing a dipole moment pointing down. As the molecule vibrates in such a fashion, the dipole moment oscillates. Degenerate to this, the nu sub v, the nu sub 2, an out-of-plane symmetric bend. The same thing happens, except one starts with a linear CO2. The oxygens bend backwards, giving a dipole pointing backwards. This oscillates as the oxygens bend forwards, giving a dipole moment pointing to the front. So the dipole moment oscillates front to back. Both modes are IR active. Raman spectrometry requires that a vibrational mode has something called an oscillating polarizability. This is attained through stretching modes. In nu sub 3, which is a symmetric stretch, your linear carbon dioxide retains shape, except first the oxygens stretch longer, which weakens the bond, makes them more polarizable, and then the stretch is reversed and the oxygens draw closer to the carbon, where the shorter length of the bond increases the strength and gives a low polarizability. Nu sub 4 is an asymmetric stretch where first the left-hand oxygen goes towards the carbon, lowering the polarizability, and the right-hand oxygen moves away from the carbon, increasing the polarizability. At the opposite end of this stretch, the left-hand oxygen moves away, the right-hand oxygen moves closer, and the polarizability oscillates between the right and the left, making this band also Raman active. So in the end, Raman spectrometry and IR spectroscopy are complementary. Molecules have multiple modes of vibration. For linear molecules, this is 3n minus 5. For nonlinear molecules, 3n minus 6, where n is the number of atoms. Each mode of vibration is different. A mode may produce an oscillating dipole, in which case it is called IR active, an oscillating polarizability, which is Raman active, or in certain cases, both. Therefore, performing both IR spectroscopy and Raman spectrometry gives a complete picture of the vibrational modes and the structure of a given molecule. In addition, Raman has unique uses. Most importantly, homonuclear bonds are nonpolar and therefore do not produce an oscillating dipole upon inversion. They are only Raman active. Only Raman spectrometry can examine carbon-carbon bonds, therefore, such as bonds found in polymer backbones and also in diamonds. This is turned into something called Raman microscopy. Since only Raman can detect carbon-carbon bonds, computer software can map the location of these bonds in a given sample. A pictorial micrograph is therefore produced, which allows for the simultaneous quantification of polymer composition and also morphology and shape, which is useful for many structural properties.